Quadratic functions. In your standard Year 10 advanced course, you will have met the solution of quadratic equations. However, those that cannot be solved are just normally dealt with by writing no real roots. Quadratic equations may have two distinct real roots, two coincident real roots, sometimes referred to as one root, and these are the two situations that you deal with in the advanced course. However, we can have two complex roots. They may be purely imaginary, i.e., it's a complex number with a zero real part. When a quadratic equation has complex roots, they occur as conjugate pairs. That's provided the coefficients of the quadratic are real. I don't think you're going to meet any where they're not. What do we mean by a conjugate? Well, the conjugate of a plus bi is a minus bi, i.e. the real part is the same and the imaginary part is opposite in sign. If we consider the quadratic equation, ax squared plus bx plus c is 0, and as discussed over here, we would have a, b and c as real constants. It can be solved using the quadratic formula. X is negative b plus or minus the square root of b squared minus 4ac all over 2a. The nature of the roots can be discerned by consideration of the discriminant. That's the part under the square root. So the discriminant, which is usually given this triangle symbol, is equal to b squared minus 4ac. You can see just here that it appears underneath the square root. So if b squared minus 4ac is positive, we get two distinct real roots. We know we can take the square root of a positive number, absolutely no problem at all. If b squared minus 4ac is equal to 0, we get two coincident real roots. That's because here we have this plus or minus, and we'll be plussing or minusing 0, and therefore the top is still negative b, whether we add 0 or subtract 0. If b squared minus 4ac is less than 0, we get two conjugate complex roots. Now, why is that the case? We know that we can't square root a negative in reals. We can only do that if we go into imaginaries. So in this situation, we're going to get an imaginary number here when we square root the negative. If the b in the equation, that's this coefficient just here, is equal to 0, the roots are purely imaginary. And you can see why that's the case. I'm just going to clear everything. You can see why that's the case when we look at the top here, in that this part here is real, and then if we take the square root of a negative, this part is imaginary, so we end up with minus b plus, let's say the square root of that is ci, and negative b minus ci as the two roots. So, in other words, we end up with a conjugate pair. If the b is 0, then we just get ci and negative ci. Graphically, the situation looks like the diagrams below. So this is b squared minus 4ac is positive. We get two distinct roots. And the roots are where the curve of y equals ax squared plus bx plus c crosses the x-axis. Remember, the x-axis is where y is 0. So ax squared plus bx plus c equals 0 gives us the points where this crosses the axis. If we have the situation where the discriminant is equal to 0, we only get the 1 point, so it just touches at that point. When b squared minus 4ac is less than 0, this is where we get complex roots, and note the curve doesn't cut the x-axis at all. All of the above diagrams are for a is greater than 0. The curves are upside down for a is less than 0. So when we talk about the a there, we're talking about in ax squared plus bx plus c. If the a is a positive number, then we get what's known as a happy curve. It's actually called concave up, but I always call it happy. If a is negative, it goes the other way. It's sad. This is actually called concave down. So if we drew those on there, you just get this. So we've got the two roots. Here it would just touch. So you've got the one root or two coincident roots. And here it would miss altogether.